Hi everyone, welcome to my channel. So in this video we are going to start the chapter mechanical properties of fluids. Okay, prior to this we have already discussed mechanical properties of solids. Okay, now see, states of matter, it is of three types. Okay, three types of states of matter: solids, liquids and gases. Okay, now many of you might be thinking that there is also a fourth state of matter, that is the plasma state. Okay, but basically at high secondary level we will not talk about this plasma state. Okay, we will be talking about these three states: solids, liquids and gases. Now we have already discussed mechanical properties of solids in the previous chapter. Okay, now this chapter is about mechanical properties of fluids. These liquids and gases, they are called fluids. Liquids and gases, they are called fluids. Okay, now why they are called fluids? Because this word fluids, it has originated from the term flow. Okay, both liquids and gases, they can flow. Water can flow, river flows, gases, they flows. Okay, air flows. Correct? So liquids and gases, they can flow, hence they are called fluids. So in this chapter basically we are going to study about mechanical properties of liquids and mechanical properties of gases. Okay, basic, and from that also, if I say most of the discussion will be concentrated on this liquids. Okay, mechanical properties of liquids, but liquids and gases together, they are called fluids. Okay, now fluids are quite different from solids. Okay, so fluids, when I am saying fluids, that means I am talking about liquids and gases. See, solids, they have a definite shape, but fluids, they don't have a definite shape. Liquid, it doesn't have a definite shape. When you pour water in a glass, it takes the shape of a glass. When you pour water in a tumbler, bigger tumbler, it takes the shape of the tumbler. Okay, so basically they don't have a definite shape. And moreover, gases, when they are put in a vessel, it occupies the entire volume of the vessel. Okay, so these are some basic differences between fluids and solids. Now another important difference between this fluids and solids is, like this, in this liquids also have some similarity with solids. Like for liquids and solids, if you change the pressure, the corresponding change in volume is quite small. Change in volume is small. This is for liquids and solids, because molecules are closely packed. In liquid and solids, the molecules are closely packed. So because of this, when you change the pressure, the corresponding change in volume is quite small. Whereas for gases, now for gases, molecules have wide separation. So when there is a change in pressure, the corresponding change in volume is quite large. Okay, so this is one observation between liquids and solids with respect to gases. Okay, acha. Now with respect to elasticity, you have a property called shear modulus. Now this elasticity, modulus of elasticity, it is defined only for solids. It is not defined for fluids. Okay, now shear modulus has something to do with tangential stress. Okay, it is tangential stress by tangential strain. Okay, so shear modulus is not defined for fluids. That means fluids, they cannot sustain tangential stress. Okay, so this is one very important feature, that shear modulus is not defined for fluids. It is defined only for solids. Okay, it is not defined for fluids. That means shear modulus is not defined for liquids. Shear modulus is not defined for gases. Okay, so these are few comparison between fluids and solids. Acha. Now, to understand the mechanical properties of fluids, we need to understand a few basic terms associated with the mechanical properties. The foremost among them is pressure. Okay, pressure. So pressure denoted by the symbol capital P. Now pressure, it is force per unit area. This is the normal definition of pressure. Pressure is force per unit area. This fluid pressure is always normal to surface of contact. This is one very important feature. Fluid pressure is always normal to surface of contact. Okay, fluid pressure is always normal to surface of contact. Okay, acha. Now why this fluid pressure arises? What is the cause of this fluid pressure? Okay, and how to visualize that fluid pressure is always normal to the surface. Like suppose now this room, now what is this there to suppose? This is the reality. This room is filled with gases. Okay, air, it is there, nitrogen gas is there, oxygen gas is there. So all these gases are fluids. So these fluids are exerting pressure on me, on this table, on this board, everywhere. So if I consider this object, this notebook, so fluid pressure on this surface, it is acting in the downward direction. On this surface, it is acting in the upward direction. On this surface, it is acting in this direction. So wherever there is a surface, the fluid will exert a normal force. Similarly, on this board, the fluid pressure will be in this direction, will be perpendicular to this board. Similarly, on the ceiling, fluid pressure will be acting in the vertically upward direction, normal to the ceiling. So it is always normal to the surface of contact. Okay. Now, what is the reason of this pressure? What is the reason of this force? See, molecules, whether you are talking about liquid molecules or whether you are talking about gas molecules. Now, these molecules, they are in a state of random motion. Okay, they are in a state of random motion. So when they are in a state of random motion, they will be undergoing collisions, okay, among themselves and also with the walls of the container. If it is they are placed in a container, and suppose on the wall, on this surface, they are undergoing collision. So molecules, they are in a state of random motion and continuously they are undergoing collision with this surface. Similarly, if I am talking about this surface, the molecules, air molecules are colliding with this surface too. So during the course of this collision, there is a transfer of momentum. Okay, and to understand this concept, like see, suppose this is my hand and this is one molecule. So if there is a collision, then what will happen? My hand will experience a force. And that force per unit area is called pressure. So this pressure, fluid pressure, arises because of collisions. Okay, collision of molecules. Okay, so fluid pressure arises due to collision of molecules. Okay, so this is the cause of fluid pressure. Okay, now suppose you have a surface like this. This is the orientation of the surface. Suppose dA is the area. So if this is the surface is like this. So from this side there will be molecules colliding with the surface, this area. So this will be the force exerted dF perpendicular. Why I am writing? See, d I am writing because dA, A is the area. So I am taking a small area. So dA represents the small area. So that small area is exerted by a small force dF perpendicular, because force is perpendicular to the area. Similarly, this force will also act from this side. this side also, because this is the area. So this side molecules are colliding, this side also molecules are colliding. So this side also there will be a force dF perpendicular. dF perpendicular. Okay. And so the system is at equilibrium because this side force, net force is 0. So the system is not going to accelerate. The system is not going to accelerate because there is no net force. Okay. The main thing to be observed here is, like, this is one area. Okay. If I consider another area which is like this. This area is like this. Okay. And suppose this is 2dA, 2 times this area. 2 times this area. Okay. Now see this. I'm considering same container. In that container, or say this room I am considering this one area at this particular location. Area is dA, force is dF perpendicular. Now at this particular position I am considering another area. So this area is like this. Now this is 2dA, 2 times of this area. Okay, 2 times of this area. So now again force will act on this surface in the downward direction. So this is 2dF perpendicular. Then from below also it will be 2dF perpendicular. Okay. Now thing to be observed here is, see, I have changed the orientation of the area. Here the area is like this. Here the area is like this. I have changed the orientation. I have changed the magnitude of the area. This is dA. This is 2 times dA. So this is double the area. So the force has also doubled. If you double the area, the force has also doubled. So that the ratio of the force to area, that pressure remains same. Okay, pressure remains same for a same fluid. Okay, because this is, I'm talking about the same room, this room. So in this room, if you measure the pressure at that particular point and at this point, you are not going to get two different pressure. You are going to get the same pressure. So this pressure is independent of orientation of the area. In what way the area is oriented and what is the size of the area. It is not going to depend on that. It is independent of that. Okay. So, from this observation, we can conclude that two surfaces have different area and orientation. Two surfaces have different area and different orientation. But pressure on them will be same. Pressure on them will be same. Okay. So pressure, it is not going to change irrespective of the area or orientation of the area. The pressure is not going to change. Okay. So, and another important thing is, see, so that means pressure is not depending on a direction. Pressure is not direction independent. Okay. So that is why we say that pressure is a scalar quantity. Pressure is scalar quantity. Pressure is scalar quantity. Okay. It has no direction. It has no direction. Okay. For this surface, I will write pressure as dF perpendicular by dA. Okay. For this, I can write pressure as 2dF perpendicular by 2dA. Okay. Now here what I have done, see, I have considered one small area. For that small area, I am measuring the force, I am measuring the area. Then from the ratio, I am calculating the pressure. Okay. Now, if we are assuming that throughout the force is equal, force is constant. So in that case, I can generalize this result as P is equal to F perpendicular by A. F perpendicular by A means what I have done, see, this dF perpendicular is the one small unit. Okay, so if at all places we are getting the same area and we are getting the same value of pressure, so if you add all those dF, so you will get the total force. So this is the total force and this is the total area. Okay, so this is pressure is equal to force perpendicular by area. So force perpendicular means this force is perpendicular to this area. Okay, this force is perpendicular to this area. So this is the basic concept about fluid pressure. Now regarding the units of various units of pressure, like SI unit of pressure is 1 Pascal, either it is expressed in Pascal or Newton meter square. So 1 Pascal is 1 Newton per meter square. So pressure is force per unit area, force is Newton, area is meter square. So 1 Pascal is 1 Newton per meter square. Another unit which is commonly used is atmosphere. So 1 atmosphere is 1.013 into 10 power 5 Pascal. For calculation's sake, in means most cases, you can take 1 atmosphere equal to 10 power 5 Pascal. You can neglect this term 1.013. Okay. 1 bar, this is another unit of pressure. 1 bar equal to 10 power 5 Pascal. Torr, this is another unit of pressure. 1 torr is equal to 1 millimeter of mercury, that is equal to 133 Pascal. Here this unit is important. At G is equal to 9.8 meter per second square, temperature is 0 degrees Celsius. Okay. 1 atmosphere, it is equal to 760 millimeter of mercury, that is equal to 760 torr, that is equal to 1.01 10 power 5 Pascal. Okay. Now torr, this term, why it is used? Because to respect a scientist by the name Torricelli, he was the first person who has devised or who has designed the mercury barometer to measure the atmospheric pressure. Okay, mercury barometer. So that was designed by Torricelli. So in his respect, we gave this unit. So that is 760 torr. So that torr is from Torricelli. Okay, so these are some of the common units that are used for pressure. So the next term that we are going to study is density, denoted by the symbol rho. Okay, this is called rho. Now basically density, it is a ratio of mass to volume. Okay, density is mass per unit volume. Now mass, it is expressed in kg in SI system and volume in meter cube. So density, it is expressed in units of kg per meter cube. Okay. Now density is a scalar quantity. It is a scalar quantity. Okay. Density does not have any direction. Like pressure, it is a scalar quantity. Okay. Now regarding density, there is one very important feature. Like since in this chapter we are going to discuss about fluids. Now fluids means liquids and gases. Okay. Liquids, we will consider that density is constant at all pressure. Okay. So rho is constant at all pressure. Okay, so even though if you change the pressure, the density is assumed to be constant. Okay, whereas gases, the molecules are quite far. Okay, so if you increase the pressure, obviously their separation is going to change. Now if the separation changes, the density is going to change. So here rho changes, density changes. Rho means density, so rho changes with P variation. Rho changes with P variation. P variation means pressure variation. So in gases, if you change the pressure, density is going to change. For liquids, even if pressure is changed, there is not much pronounced change in density. Okay. The reason is here molecules are quite compact, quite close in comparison to gases. Okay. So this is one major difference between liquids and gases with regard to density. Another important feature about density is, suppose you have two materials. Okay, now both are same materials, but they have different size. They have different volume, they have different mass. Okay, but material is same. Suppose this is copper, this is copper. Okay, so if you are talking about liquid, this is one particular liquid, this is another liquid. Different volume. Okay, so mass, material is same, mass and volume are different. Density is mass per unit volume, remember. Okay, and here mass is different, volume is different, but material is same. So if the material is same, density will also be same. Okay, density will be same. Density will be same. Okay, it is not going to change just because the amount is different. It is like, suppose you have water in a small glass and water in a big glass. Both the water is going to have obviously different volume, different mass, but will they have different density? They will have same density. Okay, so density is not going to change. Okay, material, as long as materials are same, then density is going to be same. Okay, so along with density, we need to read one more term, that is called relative density. Relative density. Okay, now basically this relative density of any material, it is a ratio of density of material divided by density of water at 4 degrees Celsius. Density of water at 4 degrees Celsius. Okay, relative density of a material, relative density of a material is equal to density of the material, same material, divided by density of water at 4 degrees Celsius. Okay, now obviously see density by density. So this term relative density, it is a dimensionless quantity. Okay, dimensionless, because it is a ratio, dimensionless ratio of similar quantities. It is a ratio of similar quantities, so hence it is dimensionless. Okay, another thing is, see density of water, raw water, it is equal to 1 gram per centimeter cube. That is in CGS system. In CGS system, it is 1 gram per centimeter cube. So if this is 1, so relative density will be equal to density of the material. But provided you are using CGS system. Okay, so in CGS system, relative density, RD, relative density, it is numerically equal to density. It is numerically equal to density. It is like, suppose material has a density of 4 gram per centimeter cube. A material has a density of 4 gram per centimeter cube. So its relative density will be 4. Similarly, if a material has a relative density of say 3 gram per centimeter cube, so its relative density will be 3. Okay, but see, this is equal to this provided this denominator you have 1. Okay, and 1 is, when it is 1, when it is expressed in gram per centimeter cube. If it is expressed in kg per meter cube, then this will not be 1 gram per centimeter cube. It will be 1000. This will multiply by 1000. Correct. So this quantity, relative density, it is equal to density provided you are using CGS system. Okay. So this is one another important feature. Okay. So this is the first part of the video. Okay. Please go through your NCERT and try to understand. I have explained everything based on NCERT. Okay. So after watching my video, go through NCERT and check whether things are clear to you. Okay, if there are any clarification required, please do revert back. I will discuss further. Okay, so with this I end this video. My best wishes.